So now that we have this method of slices, you remember what this says. The volume of a solid is equal to the integral from a to b of this area function. The a of x is the area of a cross section, dx. What I want to do is I want to use this to find the formula for the volume of a cone. And hopefully you remember from back in high school geometry, we actually know where this needs to end up. This is going to be volume equals 1/3 pi r squared h. All right, so let's start by getting some variables in here. I'm going to call the height of the base of my cone r, and I've got it lying on its side, so this is going to be the height. And I've drawn a representative cross section here for us to look at. And what I need to do is I need to find a formula for the area of that cross section in terms of x. Right, that's the position of the center of the circle out on the x-axis. So how am I going to do that? Well, I'm going to rely on a little geometry fact here, because what I need to do, I need to find the y value here, right? That's the height. That's the radius of my cross-section circle. So I'm going to rely on a little geometry fact here. Because this is a right cone, and because I'm drawing these circles perpendicular to the cone's axis, this triangle here is similar to this triangle here, right? And I know that triangle's dimensions, it's h and r. Okay, so what is this giving me? That tells me that x over, let's call this the obvious variable there, let's call it y. X over y is equal to h over r. And if I solve this for y, I get y equals xr over h. Okay, so that's the radius of my cross section, which means the area of my cross section is pi times xr over h squared. And that's what I needed, right? The area of a cross section at point x is this formula. So let's put that into our volume formula up here. This is going to be the integral from 0 to h, right? Because we're starting here at x equals 0, and we're going to stop out here at x equals h, of pi, and I'm gonna write this out. This is x squared r squared over h squared dx. All right, now pi, r, and h are constants. X is the only variable in this whole thing. So I'm going to take pi, r squared, and h squared and bring them out in front here. So this is pi r squared over h squared, integral from 0 to h, x squared dx. And that's excellent. I know how to integrate that thing, right? I'm going to use the power rule for integrals. This is pi r squared over h squared, x cubed over 3, evaluated from 0 to h. And now we do the substitution, right? The 0 was nice, because when I put 0 in there, that thing is just going to be 0. So this is pi r squared over h squared times h cubed minus 0. And that's just h cubed. So I'm going to get the h cubed and this h squared here. They're going to cancel. All that's left is an h. And, excuse me, I forgot to bring the 1/3 out. Bring the 1/3 out here. And what's left? Well, it's 1/3 pi r squared h. Exactly the formula that we expected to get. So if back in your high school geometry class, if you remember this formula here, pi, ignore the 1/3, pi r squared h, this is the formula for the volume of a cylinder. And back in your high school geometry, I know I did, right? If you ever wondered why 1/3, right? Where did that 1/3 come from? Well, this is where, right? It comes from this derivation right here. So we have another example here. Right? Let's see if we can find a formula for the volume of a slanted prism. We know an upright prism, that's just the area of the base times the height. Right? But what happens if this thing is slanted? Well, let's start by filling in some values here. I'm going to call the area of the base B, right? And I'm going to call this length here S, right? It's the slant height of the prism. And let's see, one more thing. We'll call the angle at which this thing is tilted, we'll call that theta. All right, so we have our formula, right, for the volume by slices, integral a to b, a of x dx. And I need to talk about these cross-sectional areas. I need a formula for a of x. So if we try doing this on the x-axis, like we've done before, drawing our lines, our planes vertical, we're going to have some problems. I'm going to get this cross-section here, for example, but then if I go over just a little bit, the length of the base down here stayed the same, but the height didn't. So the areas of my cross-sections are changing, which isn't necessarily bad, but it gets a little weird because when we get to this spot here, they stop changing and they'll be constant until we get to here, to here. Then they'll start to change again as we go over to the right-hand side. Could we do it? Yes. But it's going to be messy. We're going to have to come up with 3 different formulas and 3 different integrals, and there's an easier way to do this. Right? There's an easier approach to this. What I'm going to do instead is I'm going to make these cross-sectional planes. I'm going to do them horizontally instead of vertically. I'm going to do them this way, because if I do them this way, give or take my sketchy art skills, if we do them this way, then those cross-sectional areas are constant, right? They're always going to be B. So my formula, A of x, is just going to be B. Which makes my integral nice. This is the integral from A to B of a constant, dx. It's a constant, so I can bring it out in front. This is the integral from A to B of dx. So really the only challenge here is determining these limits of integration. Remember, we're doing this on the y-axis. So we're going to start down here at y equals 0. So this is b integral from 0 to something dx. And now I need to know what this height is, because that's our maximum y value. All right, so how can we do this? I'm just going to use a little trigonometry here, right? I drew this so that it's a right angle. So we've got a right triangle over here. This angle is theta. So I know that the sine of theta is equal to h over s, which means h is equal to s sine theta. All right, so let's put that in here, h sine of theta. Now if we do the integral, this is b times x evaluated from 0 to h sine theta. Of course, it's nice with that 0, right? We put that in there, the whole thing, that is just going to be 0. So this is b h sine theta, so not the whole thing, but the second part, minus 0. So my formula is b times h sine theta. Right, there you go. Now, we can do a quick check of this. Right, we do a quick check. If theta is 90 degrees, then this prism is upright. Right? And if it's upright, if it's a right prism, we know the area should just be the base times the height. Well, is that what we get? Right? Well, when theta equals 90 degrees, the volume is BH times the sine of 90 degrees. The sine of 90 degrees, that's 1. So yeah, my formula is giving me the value that I expect there. And we can test the other end as well. When theta is 0 degrees, then the height is 0. It's lying flat on that xy plane. So we expect that the air, it doesn't have any volume, right? There's an area for the base, but no height. Well, is that what my formula gives us? Well, the formula says this is BH sine of 0 degrees. Sine of 0 degrees is 0. So yeah, it works there as well, right? I'm also getting the value that I expected on that side. Obviously, just testing individual values isn't a guarantee that you didn't make a mistake, but it's the kind of thing that make you excuse me, it's the kind of thing that can make you feel more comfortable with your result. So now we've seen a couple examples of how we can use this method of slices to find the volume of a solid. We're going to take the next step, right? We're going to look at a method for finding a specific kind of solid. This is called a solid of revolution.